thought we can end the day with something nice and easy, so naturally machine learning seemed like a good fit. I'm Jakob from SideFX, and I'm going to talk about PCA shenanigans and how to do machine learning in Houdini. But what does PCA stand for? PCA stands for Principal Component Analysis, and Principal Component Analysis is a versatile statistical method for reducing a cases by variables data table to its essential features, called principal components. Principal components are a few linear combinations of the original variables that maximally explain the variance of all the variables. Interesting. Don't worry. It's basically just a math and statistics tool and commonly used in machine learning dimensionality reduction. I will now give a short primer, but don't worry if you don't catch all the details. I will go over specific examples in the following slides. Imagine you have some wine bottle standing in front of you on a table. You can describe all of those wines by different properties, like its color, how dry or sweet it is, how strong it is, how old it is, and so on. We can compose a whole different list of the different characteristics of each wine, would look something like this. But many of these will measure related properties, and so will be redundant. If so, we should be able to summarize each wine with fewer components. This is what PCA does. Instead of say 10, you may end up with maybe 3 components that describe your data accurately enough. It's never 100%, but you can get away with a lot. PCA is not selecting some characteristics and discarding others, but instead it constructs new characteristics called components. And those components turn out to summarize our list of wines very well. Those are linear combinations. In fact, PCA finds the best possible characteristics to describe the data. Those components are ordered by importance, which comes in handy later. In 2D, this could look something like this. You have 2 axes, color and age, and you have a scatter plot of all your different wines. This is, of course, not how wine works, but let's just pretend it gets more colorful over time. If those 2 properties are related, like that, you can compress them because both properties store the same underlying information. Something changes over time. The first PCA component for the data looks something like this. It's the direction through the data where you have the most variance, the longest distance, you could say. The second component would look something like this, perpendicular to the first one, second most important variance. What you can then do is project your original data samples onto the new components and calculate weights. How much of which component do you need to reconstruct the original data points positions? In 2D, this isn't very useful and doesn't compress anything. But in high-dimensional space, you can compress your data a lot, but humans are not very good at visualizing high dimensionality in their brains. It's not important to understand the math completely, but more how to use it and what this is good for. So how is this useful for CG? Say you have a point cloud where you want to fit a bounding box around. You can use the first PCA component to construct one axis, and then the second PCA component for the second axis, and the third one, and that looks quite familiar, pretty much like a transform. You can use that to lock your point cloud in the origin or fit a bounding box around it. Pretty neat, but the bound sub can do that too. So is that it? No, you can actually use PCA to do some de-jittering, like de-jittering a simulation over time. You can see here how you have lots of jittering going on that can be removed using PCA. To do that, you merge a bunch of frames over time all together. Let's say uneven number of frames, maybe 3 from the past, the current one, and 3 future frames. This is basically the main control you have about how much jitter will be removed. And now we need to make like a little mental jump. Before, all of our samples were in 2 dimensions on the wine chart. Now our dimensions are basically a high-dimensional vector that is composed of all the different point positions of each mesh. So you have 7 meshes, and each one is a PCA sample and consists of all the point positions. I put in those brackets here. PCA then analyzes this data, and then you can project your original point positions back onto it and basically reconstruct a point cloud that looks something like this. And you can think of this as the best fitting blend shape of all those inputs you had before. And if you reapply all those point positions back to your original geometry, you end up with this Maybe you can spot some issues around the hands. When he's clapping, they get stuck in the air. This is happening because you're also de-jittering the animation. So if you have fast-moving animations or lots of direction changes, this gets smoothed and cut off as well. To counteract that, you can also de-jitter a guide geometry that doesn't have any jittering on it. And then you take the difference of this de-jitter geometry and the original one to point deform your cloth back to the correct animation position while still maintaining the de-jitter result, which is pretty useful in many cases, I think. You can do the same thing on volumes, which is pretty neat if you have retiming issues or interpolation artifacts. And the setup is pretty much the same. You just need to make sure that all the volumes you feed into PCA have the same size and are native Houdini volumes, because VDBs are not supported yet. Also, one neat little trick is you can use this VEX snippet to apply a weight decay. If you computed multiple components, you can then multiply those with your weight decay to really adjust using the ramp how much of the original information you want to bring back and how much you want to remove. It's nice to dial in a good balance. Another project I was working on was the machine learning deformer, using only the new 20.5 machine learning nodes and no code, which was pretty cool. In this project, I trained a machine learning model that predicts the correct guide deformation based on a rig position. This is not a dynamic simulation, but something in between of the original guide deform that is a purely linear deformation and the simulation, basically. A common issue you run into when you do deforming grooms is that you run into intersections. You can see here how the hair above the joint pierces through the hair on the bottom, because you don't have any understanding about how much volume you're actually deforming. It's just guide curves and they don't know much about each other, and there's not enough to really simulate this volume. The ideal way would look something like this, where you get nice layering of all the hair curves and no intersections. The other two positions showed rest guides and how the displacement would have to be applied to those rest guides to avoid any intersections. So this is the ideal case we would want to be training for. To do this, you can build a whole data pipeline and training pipeline inside of Houdini that starts by setting some joint limits on your joint, and then you generate poses based on those joint limits. It's just a bunch of random poses for your character or creature. And for each of those poses, you're going to simulate the correct guide result. This is usually computationally pretty expensive. That's why you want to learn how to do it faster using machine learning. You can then compress this again using PCA into a subspace. You store this in a data set as machine learning examples, and then you can do the training in TOPS using some new nodes. The whole thing is very much based on the machine learning muscle deformer that was released on the content library with 20.5. And if you're interested in the original version from 20.0 that didn't use any of the machine learning nodes, there's a cool talk from FMX this year by Bogdan Lazar, where he went in depth on how he used the machine learning deformer on 2 projects. So the first step, as I said, is setting some joint limits, and then there's a new sub, the ML pose generate. It's just a utility sub that helps you generate a bunch of poses. What you get out of it is basically a huge cloud of all your rigs that are rotated in different orientations randomly. You generate, let's say, 5,000 poses and use those to then simulate the correct result. This simulation step could almost be anything. Here I'm using a combination of a quasi-static CAD simulation and a de-intersection pass, but really there's only one limitation, that it has to be deterministic or procedural, so quasi-static, and you can't have any inertia, something like jiggle, overshoot, or any of the simulation dynamics, so to say. As a first step, I'm turning the groom into a VDB and then into a TED cage that I'm going to use to simulate the guides. In a second step, I'm planning from a neutral position to the current pose I want to simulate. This will be the animation that you feed to the simulation. Then you simulate your TED deformation, which gives you those nice collisions that you can't really achieve using just so few hair guides. And if you apply this to the hair curves, you can see how all those jagged edges on the top get smoothed out and the volume gets preserved really nicely. This is the ideal result we want to train for. In an extra step, I'm turning the groom into a velocity field to de-intersect it. You basically mix the normals of the skin and the tangents of the guides and build a velocity field, and if you advect the guides through that, it's a nice little CFX trick. I think it's pretty commonly known to de-intersect and get rid of some intersections in the geometry. After that, you end up with your 5,000 generated example files, but those are pretty hard to store because you store basically 100,000 groom points per example, and no machine learning model, at least on our hardware, would train on that. So you need to compress that in a way. The first step is to basically extract the difference of your original rest position and your new guides that we simulated correctly. And I used the shape diff node here, just a little bit esoteric, I feel like, but does the job. Basically just subtracts the points from each other, and then you end up with a nice point cloud. This is the displacement you need to apply to all your guide points to return back to the correct result. Then you store this together with the rig in a machine learning example. There's a new sub, ML example, that's also a utility sub that helps you store data pairs together, and you double pack them. Basically, you pack the input and the target, and you double pack it again to make sure you never really get out of sync while doing training or further processing of them. After you've exported all of your examples, you load all of them back and then feed it to PCA to compress all of those 4,000, 5,000 examples to fewer components. You can think of that as before, as generating new blend shapes that best predict the data you fed in, and you can basically reconstruct all of your 4,000, 5,000 displacements from fewer components, which is pretty cool and helps a lot. In an extra step, we are then comparing each displacement to our PCA components, which lets us calculate some weights. Those are like blend shape weights. How much of each of those components do I need to return to my original displacement? And this is what we are storing in the machine learning sample. So we are compressing our 100,000 point positions down to just those 512 or 1,024 weights, which minimizes the need of data you essentially have. On the other side, on our input, we serialize the pose. Usually, rig position is a 3x3 matrix, and machine learning models don't really like this kind of input as data, so we need to serialize it in a way to store each of the values of the matrix in a single point, so we can feed it in that fashion to the machine learning model. So you have two lists of values, basically the rig data and the value chart and the weight. And then you can use the ML example output node, which basically stores a dataset raw file on disk. It's also really convenient compared to how you had to do it before. And then start training. Training is done in TOPS using the ML regression train node. It's a new node that carries the most weight of the whole system, and there's a wraparound PyTorch in the back. The best thing about this is you don't have to write any code. You just point it to the data set you wrote out, and then you have the usual machine learning parameters, which, because you're in TOPS, you can wedge them and test different parameters to see how the results turn out. One thing I like to point out is that there's many convenient features, like splitting your data set in training and validation data, which is a common thing in machine learning use cases, because you don't want to train on your validation data, because you run into the issue that your model will memorize all of your inputs and not really learn to generalize well. The thing that happens under the hood, like this is the unlocked HDA now, is you're basically generating a Python environment and installing PyTorch and Onyx and different libraries that you need for it, but you don't need to do any of that. It just happens under the hood for you. After training, you will end up with an Onyx file. And now we need to do everything we did before to prepare our data in reverse. So you have a new rig position you want to predict the groom position for. You again will serialize it, feed it to the ammo regression inference node, which applies the model to your new data, and then receive back some new weights. Those weights you give to the PCA node, which reconstructs the displacement based on the weights and the components you calculated earlier. If you apply this displacement to the rest guides, you will end up with this not so nice looking groom in rest position, but if you move it to the correct pose, you will see that it maintains the shape much nicer than the original one. I have a run cycle here, so maybe a little fast, so I'm going frame by frame and blending back and forth between the default guide deform and the results you can achieve using the ML guide deform. I also have a full groom. Here it's sometimes a little harder to tell what's really happening, but behind the head you can really tell before where you had the intersections and would get dark spots in your rendering, which don't remain after the ML displacement. Here are also some rendered frames. I also circled the problem areas you usually run into. A third project I was working on was ML sketching, or teaching Houdini how to understand your drawings. That was more of a fun one. And essentially, the main idea is to give the user a drawing UI where you can sketch outlines of some shape that drives geometry generation. This looks more fancy than it really is, because in the end, you're only predicting parameter values. So you use a neural network to learn from sketch to the right values, which you can then feed to an HDA that generates your bottle geometry. This could be pretty much anything. You just need to make sure that all those parameter values are really descriptive and not repetitive. For the generator, I went with the way using compiled blocks, because you can reuse them at multiple points in your network and don't have to unlock HDA, save it again, and it's all live, which makes it really handy. For the parameters, I used the attribute adjust dictionary, which lets you create a dictionary. And in the compiled block, I'm reading the values of this dictionary and distributing them to the different nodes that generate the geometry. Also, one interesting thing maybe is that I'm remapping those values that usually come in this case, in a -1 to 1 range, using sigmoid or cubic functions. This is because this lets you control, when you later randomize the generator to generate all your different bottle shapes, how your distribution ends up looking. If you leave it like a linear -1 to 1 range, you have all sorts of bottles all the time, but sometimes you want more neutral bottles to focus your machine learning model on that part of the data. So using those, somewhat like an activation function in machine learning, lets you control how much of what kind of bottle shape you generate. Another nice tidbit is using packed folders. Those are stolen from the character workflows and were recently introduced, I think 1 or 2 versions ago. And I think they are really useful for all sorts of setups. What you can do here is if you have multiple outputs on your HDA, and this could really be a pretty high number, I guess. So you feed those into the right input of the packed folder, and then you name them. This basically gives you an on-the-fly dictionary that you can later unpack by the name and access the different types of data you wanted to export using this generator. This time, the data generation doesn't happen in TOPS, but in a for each loop. So we are randomizing that dictionary I was talking about. This gets fed to the generator that invokes this compiled block. And that one spits out all of our different geometries. So the bottle geometry, the outline, and the parameter dictionary. Then we can use the unpacked folder to distribute those different types to the right outputs. And we're also using some cops to rasterize the outline into a 64 by 64 volume. Then we are doing, again, some PCA on those images. So we have like 10,000 images of different bottle shapes, and we want to compress them. I went with 64 weights in this case, so 64 components of this will be generated. And if you try to reconstruct based on those 64 components, you end up with something where you can make out the bottle shape, but you run into some issues where it looks kind of like a noise-ish thing, which isn't great. So Mikhail had a really cool idea to do it on SDFs instead of black and white 0 and 1 values. And that worked really great. So we used the new mono to SDF workflow from COPS, turned our volume into, or our 2D mono volume into a SDF, and then did PCA on that. And if you reconstruct based on those 64 components, you get a really nice smooth transition. That's because you don't jump from 0 to 1 instantly in your data, but you have like gradual increase of values, which works much, much better. Even 32 components looked good. The cool thing about doing PCA on those 2D images is that you can really visualize all the components that you get. So here, those are all the components, and as I said, they are ordered by importance. So the first one, you can still somewhat make out, oops, no. You can still make out the bottle shape, and the further you go, the less and less meaningful they appear, until that's almost only noise, but it's still somewhat wavy. That's because those are linear combinations of all the bottle SDFs, and this maybe reminds you of Chladni patterns, which are linear combinations of periodic functions. This is not super related, but I thought it was a nice tangent. It's maybe more understandable for CG people. If you then take an input of a user, say someone wants to generate a bottle in that shape, then you can weight all your examples, or all your PCA components. That way you can really visualize how much of which component do you need to rebuild the original shape. And if you do that, you can merge all of them together, add them, and end up with that shape in SDF form. So our training data consists of an outline that gets turned into an SDF. We do some PCA magic on that and calculate the weights. And those weights will be used to reconstruct that SDF. The weights is our input for training. And we also store the parameter values, which we generated in our generator. And this will be our target. On the side, you can see each bottle shape that corresponds to those parameter values. We again use the ML example node and the ML example output node to store our data pairs on disk, and then we can take the dataset raw file, put it through the ML regression train. This was basically done on the default settings. And after about 1 or 2 minutes of training on those 10,000 examples, you have a model that can pretty much predict bottle shapes, because you're just mapping a few numbers back and forth and not learning real geometry. On the way back, we again do everything in reverse. So we take a user input, we map it to an SDF, we take the SDF and let PCA compute the weights that are based on all of our PCA components. Then we take the weights, feed it to the ML regression train, inference node that takes the model and maps those weight values back to the parameter values, which we store in a dictionary. Then we can give this dictionary again to our generator and get our bottle back. And you can do fancy stuff like this and combine it with TOPS. Dixie and other intern built a little COP setup that automatically, procedurally shades all of those bottles. I had some interesting users. Like I showed this to my colleagues and they went straight to draw some squiggly lines, and I was going furious because obviously the whole thing is constrained by what your generator can do. So you can draw pretty much everything or anything, and you will always get some sort of bottle back because you're limited by the -1 to 1 value range. This can be a good thing depending on who is going to use this, but ideally you would want real creative freedom for the people. One idea that came to mind was, instead of predicting parameter values, because the SDF idea worked so well, predicting the whole 3D SDF, which you can also compress using PCA, so you're just predicting some weights. this is basically what we're doing here. So you map one pair of weights of your 2D SDF to some other pair of weights of the 3D SDF. And in the middle, you have a machine learning model that predicts the whole thing. That works really well. So you can draw squiggly lines and get the correct geometry out of it. You just need to make sure that you have two generators. So you generate on the one end different model outlines and the corresponding 3D SDFs, and then you take the 3D SDF after inference, like the process of applying your machine learning model. You have another converter that turns this SDF into geometry. In this case, I'm using a combination of turning this into a VDB and then projecting some geometry onto it that has like clean topology and UVs. I think, as you can see, you can also add to a drawing, so it's not limited to one line. You can keep adding pixels and pixels and we'll keep on predicting, which is really neat. There's pros and cons to both of those approaches. The good thing about the HDA or procedural generator approach is that you're basically running at real-time frame rates because you're not doing much after inference. You get very predictable results. It's extremely easy to generate training data using tops to wedge, but it's very, very hard to think of all the edge cases and user inputs while maintaining a low parameter count that describes the shape efficiently. Here are some other examples. The pros and cons of doing it on the SDF can be a bit slower, but you get like those happy accidents because every pixel or half pixel you add to the drawing will still have an effect on the output that before maybe would have been lost because you map it to the -1 to 1 range in the end. The data generation setup can be much more involved because you're not limited by the generator that you have, so you can generate all sorts of SDFs and predict those as long as you find a way to turn them into 2D shapes for your inputs. Some takeaways. I think there's diverse use cases for PCA and you don't have to be afraid. You don't have to understand the math completely. You just need to know how and when this could be useful and have it in the back of your head if you come across one of those situations. There's also simplified ML data generation using the new ML subs that does a lot of the boilerplate work you had to do before. And you can now do no-code machine learning training in TOPS. So building artist-friendly tools is much easier. And also it's nice to start small and enjoy the little setups. You don't have to start using image generators and train your own LoRa's and whatnot to do some machine learning in Houdini. I want to thank Viana for all the support. She's my manager. Mikhail, the developer, he sits in the second row here. We can maybe ask him some questions later. Lorena for the groom and wolf model. Kai, Lisbeth on the CFX team. Dixie for the COPS texturing. Attila for the pyro simulation examples. They all work at SideFX. And Wild Capture, a company specialized in volumetric video that provided the cloth simulation examples I showed in the beginning. If you have any questions, and we have time, I think so, ask me. Otherwise, I'll be around, and thank you so much.
Thank you, Jakob. Just a sec.
Awesome presentation.
Thanks.
On your vision, are we going to be able to predict volume simulations?
Would defer that question to the gentleman in front of you, but I think it's pretty hard and computationally expensive.
If we can predict volume simulations.
Predict volume simulations. You can approximate certain simulations as long as they're you can approximate certain simulations as long as they are quasi-static, so they're not time dependent, and as long as they're smoothly depending on the input. So if you have certain simulations that wildly vary as soon as you start to vary the input a little bit, then this type of machine learning won't do much good for you. So it kind of depends on the case.
Thank you. Yeah, the case I'm thinking is that with AI and the image creation, I can ask, for example, generate me 10 images of 10 silhouettes of explosions or silhouettes of smoke simulations, and those simulations, they probably have like, this is not the first frame, right? So I'm just thinking, can I provide a middle frame of that simulation and maybe get a setup that's kind of give me that look? That's kind of what I'm envisioning when I'm asking that type of scenario. Yeah, thank you so much for the answer, though.
Yeah, it like there was another question there, right? So it really depends on a case. Like we've also done some experiments where you have like a bunch of quasi-static simulations, but you didn't do the full simulation. So you had like a whole bunch of frames coming in, but you only did 1/5, for example. If you do only 1/5 and you then train on that, then you can like complete your simulation and get something that's close to doing the entire simulation. And that way you can sometimes save some time. So that's another thing you can try. Yeah. Thank you.
Thank you so much. That was a great presentation. I really enjoyed the analogy with the wine at the start, which helped me to understand it quite a lot. And I guess this is less of a technical question, but you described how components are sort of like dimensionless numbers that represent sort of multiple different qualities or multiple different variables. So it's an optimization. Is that correct?
We can go back to the slide, maybe. I always thought the best way of thinking of it is as blend shapes. So all the 3D examples, you're basically having lots of tons of different shapes, and you're generating a few blend shapes. And if you combine them correctly, you can reach all of the input examples, or almost all of them, pretty accurately. I don't know if that answers your question.
I'll try to rephrase the question. So one of the aspects of this technique is that you have a wide range of parameters and you're somehow condensing it down to less parameters. Yes. Is that correct?
That's correct.
Okay. And I was curious if that's always an oversimplification, or if that can allow you to find a more accurate description of the parameters that actually define how something ends up the way it is.
I think you're never going to increase the accuracy. So you're always losing a tiny bit, but in some cases, like for example on the bottles, where we compressed 10,000 examples to those 64 components, you don't lose much, and you basically get to 99.9% accuracy of reconstruction while compressing it a lot. But you never get more than 100% accuracy. Is that the question?
Yeah, that's true. I guess it's, like I said, it's not so much a technical question. I was wondering if there's things we can learn from that reduction in parameters. So for example, we might have a certain degree of redundancy in the parameters that we're using to describe something.
Yeah.
Like for example, with your example with wine, we have all of these different characteristics that we can identify, but maybe that just comes from a smaller set of variables, and it's our interpretation that leads to all of these different parameters.
You're always compressing in the end, so you're losing some data, but you can get away with losing very little data while still compressing a lot, which is the magic to me. Yeah.
All right, thank you so much.
I might be able to chime in on this, and also a question, and thank you for the great talk. I think maybe I'm interpreting your dialogue here a bit differently, but I'm saying you're asking if there's something to be learned about principal components that you spit out. And yes, especially when it comes to latent spaces in neural networks, and I'll be talking a bit about that tomorrow. But there is basically the first components give you a broader general sense of direction or general sense of concept behind your data. And the further you get away from the main principal components, the fine-grained or the more detail or the more subtle things in your data show up. So that's an analogy of what it does. And my question is also very technical towards the PCA compression you're doing.
Okay.
How did you come up with the number of components that you wanted to go? Did you do an analysis or was it more of a gut feeling? How did you arrive at this number of components?
For the texturing example, or for the bottle example, or for the groom example?
Yes. Yes, basically.
Which one?
I mean, is there a process? Do you compress example data and regenerate the original data, do a delta, and then have a threshold where you decide, okay, 16 components is enough, 60, 600, 6,000?
It was much more manual. On the bottle example, I just compared the output that I got from the PCA reconstruction to what it should have been. And everything above 99.5 or whatnot is pretty much good enough. You can't tell by eye. And the same was the case on the wolf example. You could, of course, do this on top and build some loop that adds components and checks the number that you get back of the accuracy and then do it again if it's not high enough. But yeah, for me, I just dialed it in. It's pretty fast to calculate and then see if it's 99 or above, and then go with that.
All right, thank you.
Thanks.
Anybody else?
Thanks for the talk. The vase example I thought was really interesting, for playing around with those kinds of user interfaces. I think there are probably like a lot of different ways to do that with the vase. I'm curious, are there other sorts of objects or extensions to that you've thought about that you think would be other ways to apply similar techniques?
I did an example with castle towers, but we decided to go with the very simple vase example because it's the most straightforward, I guess. It works really well for stuff that revolves, basically, and or for things that have a very clear silhouette side view. So I could imagine this working well for a boat generator, where you basically draw the outline of the bottom half of the boat, and then you generate based on that if you have an HDA that does that. I think it gets tricky if you have really involved shapes that can be vastly different, but it's the case with, the problem is building the generator, I guess. Usually, for procedural problems, you always want some with which you, or inside of which you operate. Does that answer your question?
No, yeah, that's helpful, thanks.
Thanks.
Anyone else? Okay, that's it. Thank you, Jakob.